Good morning, everyone from Europe. So particularly our speaker, Prof. Ingrid Mertig. And good afternoon to friends in India or Asia and subcontinent. It's my real pleasure to welcome you to this W2A seminar, webinar series on spintronics. I'm really happy and privileged today to formally introduce Professor Ingrid Mertig, whom I know from very long time. I think many of us know her work. She is very popular in the field of spintronics. Really does not need any introduction, but as a matter of formality for the benefit of our young students, I like to just briefly tell about her academic career. So she is now working at Martin Luther University in Halle, Wittenberg, in Germany. And her education, she obtained her diploma in theoretical physics from Technical University Dresden, also PhD from the same place. Then she was in Russia in the Joint Institute for Nuclear Research for about 5 years between 1985 to 90. And in 1995, she got the highest academic degree, that is habilitation in Germany, also from TU Dresden. Then she was working as an assistant professor in TU Dresden from 1982 to 85. She was a senior scientist at the Joint Institute for Nuclear Research in Russia and a regular guest scientist at Research Center Ulis in Germany from 1990 to 95. She has visited many places as a guest professor via her sabbatical, for instance, at New York University in US, University Paris Sud in France, University Nagoya, Japan, then Bristol University in UK, Riken Center in Tokyo, Japan, and so on. She has been very, very active in different professional activities. For instance, she was the spokesperson for 6 years between 2001 to 2007 in the DFT research unit oxidic interfaces. Then she was also the member of the nomination committee of the Gottfried Wilhelm Leibniz Program Advisory Board, and so on. She is member of the German Council of Science and Humanities, Advisory Board of Helmholtz-Zentrum, Dresden-Düsseldorf, and so on. She has been awarded many recognitions and honors to her credit. For instance, in between 1997 to 2000, she was the Heisenberg Fellow of the DFG. In 1999, she was the Fellow of the Japan Society for Promotion of Science. And between 2007 to 2018, she was a Max Planck Fellow. Her research interests actually manifold: quantum theory of solids, density functional theory, transport theory, theory of magnetism, physics of nanostructures, spintronics, topological properties of solids. And I think today we will hear the combination of spintronics with topological effects. And on behalf of my committee, my co-convener, Dr. Brajbhushan Singh, and other members of my WTS team, Puspendra, Shakti, Ajat, I again welcome you all. And I request now Ingrid to start her lecture. I just want to mention that during the lecture, we don't take any questions. So if you have any questions, kindly write that in the chat box. At the end of the lecture, we will definitely take the questions. Thank you so much. And Ingrid, it's all yours. Thank you.
Thank you very much for the kind introduction and welcome everybody. I don't see you all, but I hope you hear me well and you see my slides. And the topic of my talk today is indeed the connection of topological properties and transport properties, in particular the transversal transport properties, which are the Hall effects. So after a short introduction, I will talk about the topological Hall effect, the anomalous Hall effect. I have a certain issue here in coplanar antiferromagnets. Then if I have enough time, I will also introduce the so-called magnetic spin Hall effect, and this is the end of my talk. Yes, transversal transport coefficients. So transversal, usually if we apply an electric field, the transversal response is in combination with a magnetic field or a magnetization, and then we observe the Hall effects. And this is the standard Hall effect everybody knows from electrodynamic lectures, that there is a Hall effect due to the Lorentz force. If we have moving electrons in an electric field and a perpendicular magnetic field, then we have a separation of positive and negative charge to the left and right edges, as shown in my figure. Shortly after the Hall effect, Hall himself discovered the anomalous Hall effect. He did the measurement now in a ferromagnetic material, and without the magnetic field, he still had an effect. Due to the magnetization of the ferromagnetic material, he observed a bias perpendicular to the current. But in difference to the regular Hall effect, the separation with respect to the separation of the electrons is with respect to the spin. But in a ferromagnet at the Fermi level, we have a different number of electrons with spin up and spin down. For this reason, we still observe a bias. In 2004, then, the spin Hall effect was discovered, or predicted, let's say predicted. The idea was, if we don't have a magnetic material, a ferromagnetic material, but a regular metal, and we don't have a magnetization, but we have spin-orbit interaction, there might be a chance that the electrons are separated, so the moving electrons here in the current are separated by spin again. You would not observe a bias here, since the number of spins, spin up and spin down electrons at the Fermi level or at a certain energy is the same, since we have Kramer's degenerate states. So the theoretical explanation was really much later than the discovery of the anomalous Hall effect. And the background of the theoretical explanation is, in a relativistic description, quantum mechanical description, the spin-orbit interaction, or we use another concept, which is a semi-classical concept, and this is based on the Berry curvature. So in my talk, I will concentrate on, I will try to explain this in terms of the Berry curvature, although both descriptions are equivalent. So this Berry curvature occurs in the semi-classical equations of motion. And we start with what we know, the change of momentum, which is the Lorentz force term due to the magnetic field and an acceleration in the electric field, and the change of position of the electron, which is the Ehrenfest, which is the group velocity. And only in the 90s, this new term was discovered by Janyu. And you see a symmetry in the equations of motion, k dot, r dot, k dot. And in this way, this Berry curvature, its vector field, can be interpreted as a magnetic field in k-space. This is not a magnetic field that you can measure. This is a force field that acts in k-space. And this is what we want to look at. What are the consequences of this term? So the consequences of the Lorentz force term or this term are, if I start from Ohm's law, electric field, conductivity tensor, current, then I would have the conductivity tensor would have this non-diagonal elements, which are the transversal response elements to the electric field. I just jump to the formulas that I will use during the talk. I will repeat them from time to time, but the formulas to calculate the anomalous Hall conductivity is very simple. It's just an integration over the Berry curvature over all occupied states. So this is this Berry curvature field. This is the Fermi-Dirac distribution function, and this is the integral over the Brion zone. And with the Fermi-Dirac distribution function, we take only the occupied states into account. And this is the number of bands that I consider that contribute to the conductivity. And in front, I have the conductance quantum, since this is mostly a number. And this gives really the units of the conductivity. And the Berry curvature can be calculated in this way that we observe it's like second order perturbation theory. We have two matrix elements. And in the matrix elements, we have the velocity operator. And the velocity operator, the matrix elements are considered with the states, the Bloch states in my system. And in the denominator, I have the difference of the band energies. So you see, if I have band N and band M, I have this difference. And from this formula, you see already that the Berry curvature is going to be very large if the band energies are nearby. It would be singular if you would have a crossing. And another thing is that you see in this formula that the Berry curvature field is, as I said before, it's a force field, but this is the force field that you feel in the band number N. But the force field is generated from all other bands. You see, my sum goes over all other bands M besides the one I consider. So all other bands in this is the idea of the semi-classical description, that I have my electron is moving in one and the same band forever, but it feels a field from all the other electrons that are nearby in the other bands. This is the idea. So now I come to the topological case, and just to remind you of what is a topological insulator, I have shown this cartoon from one of the first papers in this field. This is the topological surface. This is the edge state. These are the edge states of a topological insulator, of a set 2 topological insulator. These are the bulk bands. And usually we would have a gap, but the edge states bridge the gap. Now, I would like to consider what happens to my conductivity tensor element if my energy would be in the gap of this topological insulator. So then I would come to the quantum anomalous Hall conductivity, since the edge states are quantized, and I would come to a quantized conductivity. And this is easy to see. I have the same formula again as for the anomalous Hall effect, but this integral gives now an integer number and multiplied with the conductance quantum. So, and the integer number that I observe is a topological invariant. So it's the so-called Chern number. And this Chern number gives you the number of edge states that you would have in the gap. And again, it's related to my, and again, this is the same formula with the Berry curvature included. Okay, now I had these figures of the Hall effects in the beginning, and now I would like to show you how these figures would be modified in the case of topological insulators. So let me start with the quantum Hall effect. I started also with the regular Hall effect, where I said it's just the Lorentz force that acts on the electrons, on the charge of the electrons. And this is the same here. I have this perpendicular magnetic field, and the electrons are accelerated in the electric field, and then they move along the edges here in this direction. But since they are accelerated, or since they are influenced by the Lorentz force, and the Lorentz force acts on the charge, both electrons with spin up and spin down move in the same direction. So you see that in my cartoon, the little arrows here of the edge states with opposite spin go in the same direction. This is the quantum Hall effect. Let me jump to the quantum anomalous Hall effect. So now this was the case with the magnetization instead of the external magnetic field, the ferromagnet. In the ferromagnet, I have no more Kramers degeneracy. I have exchange split states. So it means I have only one state, for example. I can have more edge states, but for simplicity. And either spin up or spin down. This depends on your system. But this one state, this means now it's a spin polarized current turning along the edges. A spin polarized current, since I have an electron with a charge and with a certain spin. And finally, I come to the quantum spin Hall effect. And as I said before, this Berry curvature field does not act on the charge, but on the spin. And now, since the electrons have opposite spin, this Berry curvature field courses motion of the electron spins in opposite direction, as before in my cartoon, only that these are now the edge states. And this means we have now a spin current. So there is no more charge current, since the charge current is always compensated. So the charge current is compensated, but we have a spin current. So we have a transport of angular momentum. Okay. Now I want to add something new, and which is the so-called topological Hall effect. And the topological Hall effect is related to skyrmions. This work I did together with Birger Goebel. He was a PhD student in my group. Alexander Moe, as well a PhD student in my group. He is now a postdoc with Daniel Loss in Basel, and with Jürgen Henk, who is a senior scientist in my group. So we did quite some papers on this subject. But what is the idea? We have now the measurement for Hall geometry, but the system that we want to investigate is a system with a chiral spin texture in contact with a two-dimensional electron gas here. And as a consequence, we would measure a charge current, a transversal charge current, a transversal spin current. And so the charge current would give rise to a Hall bias. So now let's consider the chiral spin texture. And this is one of the first beautiful view graphs of a skyrmion texture. It's from the group of Tokura in Tokyo. And you see the skyrmions here formed. And I now show you the view of a theoretician, our view of a skyrmion lattice. So we use the same color scale, and we have a periodic arrangement of skyrmions in a lattice. And a unit cell of this lattice would include a background spin texture, so which is characterized by the magnetic moments Mi. Of course, we can change the size of the skyrmion, but in all the calculations that I will show you, we use more than 100 atoms, so more than 100 little errors in the unit cell. And the error is a localized moment at an atom. So this is then our model Hamiltonian. The model Hamiltonian has this spin texture, Mi, and then coupling constant. And then this is a free electron system. This is this free electron, this two-dimensional electron gas next to the spin texture. And the electrons have a spin. And then they move in this spin texture under the influence of the spin texture, under the coupling. They align along or perpendicular to the spin texture. This is the idea. So, and this are some insights into the topological Hall effect. So I take this Hamiltonian and calculate the band structure. And the band structure as a function of m over t. So these are the parameters. M is in principle the length of the magnetic moments, and t is the hopping element. Sorry? Okay, sorry. Is there any question?
No, I'm sorry. I think somebody has just by chance.
Oh, okay.
Yeah. I think please continue.
So if the magnetic moments would have zero length, I would have no coupling, and then I have a band structure with manifold degenerate bands, since I have more than 100 atoms in the unit cell, and it looks like this in my hexagonal system. If I switch on the length of the magnetic moments, you see that the degeneracy is split, and the color of my bands tells you whether the spin is parallel, then it's blue, or anti-parallel to the background spin texture. And then it's red. And so I could continue, could increase this, and finally, if I go to large magnetic moments, I have a strong interaction then of the electron spin with the magnetic moments. And this is also called adiabatic limit. This means that the electron spin is really aligned or anti-parallel to the spin texture, and this gives the separation of the two blocks. So the electron energies where the spin is aligned with the background spin texture are lower. This is the blue block. And anti-parallel to the background spin texture is higher. This is the red block. But nevertheless, the electronic structure looks nearly the same. So for this reason, I will consider only the lower block for the rest of the calculation. The upper block gives the same result with opposite sign, since just this spin has the opposite orientation. So now I take my formula as before to calculate the anomalous Hall effect. I have the band structure. From the band structure, I can calculate the Berry curvature. I solve this integral over all the bands, and I get a conductivity. And this is my result. And the only difference from before is that it's now a two-dimensional system, and I have only an integration over 2D. And what I see is I start from 0, then I get a plateau, height E square over h. Then I get some little dip. I explain that later. And then comes the next bend, and I get the next plateau. Like in the quantum Hall effect, I have plateaus in integer steps. The steps are E square over h. In the quantum Hall effect, the steps are 2E square over h. So this goes further, but it's not anymore so nice to see. But you can see something else interesting. I would like to show this. If you come from below, you have 2 bends here, and you have immediately a step of 2E square over h. And so, how can I understand this result? I would like to make a little discussion of the topological Hall effect in comparison to the quantum Hall effect. I have this spin texture, and this spin texture, since it's a skyrmion, can be characterized by a skyrmion number. And this is how I calculate the skyrmion number. And the skyrmion number can also be related or courses. It depends on R, and it's called emergent field. I can analyze the skyrmion number is an integer number, but this integrand alone, if I don't integrate yet, it's called the emergent field. And this is how the emergent field looks like in the Brillouin zone. And you see this emergent field is negative and positive red and also 0. And the emergent field is nothing but a Berry curvature field. It's not really a magnetic field in real space. It's a Berry curvature field in real space. And this skyrmion number is nothing but a topological invariant, the same as the Chern number for the Berry curvature in K-space would here be the skyrmion number in real space. And the point is that I don't have only one Berry curvature. The Berry curvature is related to a parameter that I have in my Hamiltonian. And I have as many Berry curvatures as many parameters I have. And in my former example that I discussed, I considered the Berry curvature in K-space, which the parameter was K, was the Bloch wave vector. And in this skyrmion discussion, the Berry curvature is in real space, since the parameter is the angle between the individual magnetic moments if I go from one to the next magnetic moment. So now we would like to use this emergent field and consider the motion of the electrons in this emergent field. To make it a little simpler, we homogenize this emergent field in a way that the skyrmion number is conserved. So we keep the topological properties conserved, but we do not consider this R-dependent field. So now, if I have this emergent field is a field in real space, I can take it into account in a Hamiltonian. And you know it from Pire's substitution from quantum mechanics lectures. I can take a magnetic field in the Hamiltonian. I can take into account by a vector potential. And so I consider now motion of free electrons in this emergent field, which I take into account by a vector potential. And this is the result. So these are free electrons in a triangular lattice. And the result is now one band, which is this. This is the Brownian zone, the two-dimensional Brownian zone. And this is the solution for the band structure in this Brownian zone. It looks like a graphene band, if you want to say it like this. It would be without the vector potential, it would be just like a graphene band structure here. With this vector potential, you know what happens. You know what happens again from your courses in quantum mechanics. You would get Landau quantization. So the electrons would not live in full K-space, but they would condense in these Landau levels. These are the red curves here and blue curves. These are the Landau levels. And these Landau levels are here shown in the Brownian zone. So this would be a circle, a larger circle. This is a very special Landau level. It's like a hexagon. And then if we would go, this would be whole states. And here we would come to electron states, and then the levels would be closed. Here we would have these little pockets. Here we have just one level or one Fermi surface sheet in the Brownian zone, but from the pockets we have two per Brownian zone from the electron pockets. Now we calculate the same way as before the conductivity. And this is what we get. We come from above, we start and we see integer jumps of the conductivity by E square over H. If we come from below, then we have the jumps of 2E square over H. And this is clear from this little explanation that I gave. Here we have just one Landau level in the Brownian zone. Here we have two electronic orbits in the Brownian zone, so we get two contributions to the conductivity. Now, let me consider the Chern number. We calculated the Chern number now for the Landau levels. If we come from above, Chern number, this is the density of states, of course, but the Chern number would be -1 first level, again -1, but now the second level contributes, we have a jump of 2 square over H, and so on and so on, and we get very high Chern number here at this very special orbit. I don't want to discuss the details, but it's related to a Van Hove singularity. And then we get Chern number -2 from these orbits here, from these Landau orbits. So this is our standard quantum Hall picture. And now let me compare the band structure of this electron in the skyrmion lattice and the free electron in the emergent field. So the electron in the skyrmion lattice, we have the interaction. We have in our Hamiltonian, we had the free electrons plus a Zeeman term, something like our Hans rule coupling term that couples the electron spin. So the interaction of the texture with this electron spin is via this term. In this description, I have also free electrons, but they move in the emergent field. But the emergent field is related to the spin or is caused by the spin texture. So we see that the energy, the dispersion relation is quite similar. Of course, in the skyrmion lattice, I have more dispersion of the bands. They are not so flat. In this simple, we made this simplification that we homogenized the emergent field. So we have free electrons, and we have totally flat lambda levels. But we have a correspondence of each band with a lambda level. Yeah, and also here we have a correspondence of the two bands with two lambda levels. Of course, they are degenerate. You don't see that here. Now, let's compare the conductivity. Also similar. So we had this one jump 1 e square over h, 2 e square over h, 2 e square over h. Totally similar. Also here 4 e square over h. Now, how can we understand that? Let's now consider the surface dispersion relation, or the surface band structure, we call it. What is it? Before I have shown you the band structure on certain symmetry lines in a two-dimensional Brownian zone. Now, in the surface band structure, I project the bulk band structure, the two-dimensional band structure, to a surface, which is in this case just an edge. So to a certain surface that I can determine by the surface normal, and then I get this surface band structure. How do I understand the surface band structure? The surface band structure shows the bulk bands, but the dispersion from the two-dimensional Brownian zone from one band is giving rise at this. So since it's projected to the surface, it's giving rise to a real band with bandwidth. Since you see all dispersion at one edge, and so on and so on. Since we didn't have dispersion for our Landau levels, we have flat bands also, flat bulk bands also in the surface band structure. But the advantage of the surface band structure is that you see the edge states. Since the edge states are not visible in a bulk band structure, since they don't have enough weight, but here you see one edge state between the first and the second band. So this starts here and this continues here. One edge state. One level, plateau from one edge state E square over H. Two edge states, 1, 2, 1, 2, plateau 2 E square over H. So the Chern number that we calculated before tells us how many edge states we have. And this gives rise to the plateau in the conductivity, in the quantized conductivity. And here also you see two bands. Chern number was -2, and the plateau is 2e square over h. And this is similar. And if you look here, you have also two edge states in here, the red curves now. Now I can show you a little detail. Here in the beginning, I said this is not always quantized. This has something else here, which deviates from the quantized level. And this can be understood here. So here we have a contribution. Here we are in the global gap, and we have a contribution only from the edge states. In this energy region, we have, of course, also a bulk band. And the bulk electrons, they also contribute. They have this, not the quantum Hall effect, they have this regular anomalous Hall effect. And this reduces the quantized. So the electrons in the bulk move in opposite direction to the edge states. And this reduces, and this is not an integer number in the bulk, it's just a real number. This reduces the edge current. And the higher the dispersion of a band, the stronger the deviation. So the bands are quite broad, like here, you do not see the plateaus so well anymore. And you also don't have anymore these nice global band gap. To see the contribution from the edge states, you need this global band gap. So now I come again back to this figure, and I want to tell you how you can understand the quantum topological Hall effect with respect in this as a cartoon. The cartoon would be the following. You would have, instead of this material, a collinear ferromagnet, a non-collinear magnetic material. In particular, we considered a skyrmion lattice. And as a consequence, the edge states are also quantized, as I have shown to you, but the spin of the edge state is non-collinear, since the spin always, the spin of the moving electrons aligns always to the skyrmion spin texture. So, but nevertheless, it's the same as the quantum anomalous Hall effect, collinear magnetic system, non-collinear magnetic system, or even, as I have shown to you, it's nothing but a quantum Hall effect, which I considered by this Peierls substitution, by the simple model. And this gives the same plateaus as the quantum topological Hall effect. Okay. This was the first part. So I have shown you that the anomalous velocity, which was this new term in the semi-classical equations of motion, is the origin of all the different transversal transport coefficients, the Hall effects, the regular Hall effects, spin and anomalous Hall effect, and also the quantum spin Hall effects. And then I tried to show you that the topological Hall effect can be mapped on a quantum Hall effect and can be explained in the same way as the quantum Hall effect by the edge states, but the edge states have a non-collinear spin texture. Okay, let me now come to the anomalous Hall effect in coplanar antiferromagnets. This work was done with Oliver Busch and Børge Göbel. And the motivation of this work was that coplanar antiferromagnets, I show you in principle the lattice or the unit cell with the spin texture. This is a three-dimensional system, and it has along the 1-1-1 direction a stacking of Kagome planes. And these are the Kagome planes. And the stacking is so that we have coplanar magnetic moments of the atoms, inward or outward. So the next plane would be on top of this, but shifted. And we have these are antiferromagnets, we have no resulting magnetization. They have been called chiral antiferromagnets. So we have two types. The one that I have shown before, this was the manganese-3 iridium type, or rhodium or platinum. And this is a system with positive vector chirality. So this is from the lattice and FCC system with this in 1-1-1 direction, this stacking of the Kagome planes. Then there is, and if you would go around here and calculate the vector spin chirality, you would find out the vector spin chirality is positive. The vector spin chirality in this class of material, they are hexagonal, and you have a stacking along the z-axis, and this would give rise to negative vector spin chirality. So these are two types. Both of them are antiferromagnets, no resulting magnetization. And there was nice prediction of large anomalous Hall effect by the group of Alan MacDonald, and also Claudia Felser contributed to the predictions. And then there was also experimental verification of the effect, so the large anomalous Hall effect was really seen in experiment, not in all, but in many of these systems. And I come back to this first slide, and the point is that until now there was this rule of thumb that the anomalous Hall resistance is proportional to the magnetization, the total magnetization of your material. But now the magnetization is zero, and I wanted to understand why we have a large anomalous Hall resistance. So we start from a very similar Hamiltonian as before. Free electrons moving in a spin texture. But we take another term into account, and this is spin-orbit coupling. And the spin-orbit coupling term introduces the chirality in my system by this term. You find the spin-orbit coupling defines, so from the spin-orbit coupling, the electron knows whether it is turning left or right in the unit cell. And the system that I want to consider now is this so-called radial geometry that I discussed for the positive vector spin chirality. This is manganese 3 iridium. All magnetic moments are pointing outwards, and I have the following symmetry. Since it's a magnet, time reversal symmetry is broken. But time reversal symmetry in combination with mirror symmetry is the symmetry of a system. So we have 3 mirror planes, and these combined symmetries are a symmetry of the system. This combined symmetry is not enough to cause Kramer's degeneracy, since the square of this combined symmetry element is +1 and not -1. Okay, now let's go further and let's consider the band structure. The band structure of the system without spin-orbit coupling. We have 6 bands, and as I said, they are not degenerate, since this combined TM symmetry does not cause Kramer's degeneracy. So the bands are not degenerate, but we have some crossings. We have some band crossings in the system that occur only if the spin-orbit coupling is 0. If we switch on spin-orbit coupling, another thing that I want to mention, the bands have a color, and gray color means this is the spin moment out of plane, perpendicular to my Kagome plane, the expectation value of the electron spin out of plane. And without spin-orbit coupling, it's 0. All bands are gray, and this is exactly 0 for this spin moment. If I switch on spin-orbit coupling, I see, what do I see? I see that the avoided crossings are open, first of all, and then I see that the electrons, I can observe some certain out-of-plane moment of the electron spin, which is given by the color. So +1 and blue is -1. So now for this system, I calculated the conductivity, exactly the same formula as before. And the conductivity is given in units of E²/h, also as before. And I get the following figure. I see that I have positive and negative values. And I see that in case, what do I see first? I have to show you the black line. I cannot show it nicely, but there is a black line for the case that lambda is equal to 0. Then without spin-orbit coupling is no anomalous Hall conductivity, 0. With spin-orbit coupling, we observe, we measure, or we calculate positive and negative values as a function of energy. And we also observe, since we have here a global band gap, quantized values, -2, and here I have a global band gap and it's -1. It's very similar than before. And now we wanted to understand, what does the spin orbit, what happens in my system that I get this large anomalous Hall effect. Let me go back. The anomalous Hall effect in comparison to, so you can really observe large values that have not been seen in other ferromagnetic systems. So now, to investigate this, we did the following. This is the configuration I started with. And without spin-orbit coupling, everything was 0, no spin Hall effect. What I now do, I consider a tilting out of plane of my spin texture, like in the Skyrmion system. I tilt my system, my spin texture out of plane. So either in one direction or above or below tilting. And then I see that with the tilting, this 0 value, even without spin orbit coupling, is going to be non-zero. Let's consider just this, the black curve for simplicity. We have 0, and then we have a large value above and below, if we have a certain angle of tilting. Now, I do the same with spin orbit coupling, same calculation. And I see for the radial configuration, 90 degree, it's not anymore 0. We have seen that before. It's a large value. It's a large value that if I concentrate to the black curve, these are just different energies. But now we concentrate to one energy. And what we also see is that it was 0, it's just shifted to a certain angle. The angle looks like 103 degrees. So what does it mean? If the anomalous Hall effect is again 0 for all energies, this means that although I have spin orbit coupling, the symmetry that I had here, with this symmetry, the anomalous Hall effect was forbidden, the symmetry is restored by tilting. I tilt my texture out of plane up to 103 degrees, and I restore the symmetry, asymmetry that forbids anomalous Hall effect. So now I consider this again. So this is this coplanar spin texture N, and I start from my Hamiltonian, and now I do unitary transformation of my Hamiltonian. And the unitary transformation, I want to understand this large value, as I said, and the unitary transformation leads to, a unitary transformation does not change the expectation value or the quantity that you want to measure. Is just a different way of description of one and the same problem. And you see what happens after the unitary transformation. Of course, my operators are different now, but it happens that the spin texture is different, is changed, and we call that M tilde. And further on, also this hopping matrix element is changed a little bit. We call it effective. And then also the spin-orbit coupling constant is changed. And in particular, we have also the case that the spin-orbit coupling constant can become zero. After the transformation, we have an explicit expression for the spin-orbit coupling as a function of tilting angle alpha. And you see that this spin-orbit coupling constant can become zero. For the system under consideration, this coupling constant is going to be zero at 103 degrees. That is what I pointed out before. And if this coupling, spin-orbit coupling term, this effective spin-orbit coupling is going to be zero, then I'm back to the case of a system without spin-orbit coupling. But it's now a system with this virtual spin texture. So what is the conclusion? The conclusion is that I can generate a virtual spin texture that is coplanar. And for this coplanar virtual spin texture, I do not observe any anomalous Hall effect. But the anomalous Hall effect for without tilting is of course large, since I can relate it, this effect, maybe I should go here, I can relate it or explain it, this large effect, that's what I wanted to understand, is by the virtual spin texture. So the virtual spin texture means it's the same effect like a skyrmion. You have this out of plane tilting of the virtual spin texture means that you have an opening angle of the magnetic moment and magnetic moments, and this gives rise to a topological Hall effect. And this opening angle is what you also calculate for the skyrmion number. And this, so it means that the large effect that we observe in this coplanar antiferromagnets is more a topological Hall effect than an anomalous Hall effect, since it's related to a virtual spin texture. If my system, if I include spin-orbit coupling in my system, it's related to a virtual spin texture that is not coplanar. Okay, and I think this is the end of my talk. Let me summarize. The microscopic, I was interested in the microscopic origin of the anomalous Hall effect. And our analysis showed that spin-orbit coupling causes a virtual spin texture that is responsible for the Hall conductivity, instead of the spin texture that you would measure by neutron scattering. And this virtual spin texture gives rise to something that is more a topological Hall effect, which is proportional to the opening angle of the magnetic moment, and an anomalous Hall effect that is proportional to the resulting out of plane moment. Okay, I think this is the end of my talk. Let me, I skipped this. Let me thank my collaborators again. We have collaboration with many people in Germany and internationally, and I would like to thank them. Thank you for your attention.
Yeah, thank you so much for this very nice overview of these interesting topological effects. So I clap on behalf of everyone. So it's time now to take some questions. But before that, I like to request Ingrid to switch off your screen. I mean, to stop share the screen. We will take a screenshot. So I request everyone to switch on your camera if it is possible. We will take some screenshots and then we will come back to the the question. So yeah, great. So I take gallery view. So I would request you to smile if possible. Smile. And I will take the next screenshot. And many people. Okay. So many of the colleagues have not switched on their camera. All right, I respect their decision. Arvinda came up, so we'll take one more photo. So smile. All right. Thank you so much. So I request you all to switch up your camera. And Ingrid, kindly share your screen again because there are maybe some questions for which we need your PPT. So until now, I don't see any questions. So I would start with. So as you may know that recently there is a big discussions going on about the validity of topological Hall effect for thin films. So for multi-layers where we have the Nels fermions, there has been several people reporting, but there are also some people debating if it is really the true topological Hall effect, which you get from, let's say, bulk samples where you have fermions. So what is your opinion on that?
You mean topological Hall effect in multi-layers?
Yes, yes.
So that I have a stack of multi-layers, so
Yes.
Skyrmion layer and then some layer in between.
Yeah, so basically in some multi-layers with ferromagnet heavy metal systems.
Yeah. So actually we have been part of such investigation, and my opinion is that this topological Hall effect also exists, and it could be related to the number of skyrmions that you have in your layer, in your system. It's related to the skyrmion density, and I think, yes, it exists also in a multi-layer.
Okay, that's good to hear because we are measuring that and there is some controversy about it. So thank you very much. And these, before I ask, I take questions from others. So I think Professor Mahendran from NUS, Singapore. Mai, you want to ask yourself?
Yeah, how can we experimentally distinguish between the anomalous Hall effect and the topological Hall effect?
No, experimentally you cannot distinguish. You measure always, so I calculate always one and the same thing. So I have shown you, my calculations have been always one and the same formula. And you would measure, you would get a signal, and your signal is a conductivity signal or a bias, a Hall bias. And so you wouldn't know why it is large or why it's not so large. But so you would not be able to distinguish that. The only thing that I could say that if you are sure that your system is collinear, then you would not have any topological Hall effect. Topological Hall effect is really related to non-collinearity.
Okay, thanks.
Okay, Professor Saival Basu.
This virtual spin texture, can you measure it by neutron diffraction, or is it a dynamical effect, which is, if I do a static neutron diffraction experiment?
Yeah, you would see the black. The virtual spin texture would not be seen in a neutron scattering. The virtual spin texture is something that develops in your system under spin-orbit interaction, but in neutron scattering, you would really see the coplanar texture.
Okay, so the coplanar texture I can see.
Yeah, the black, you would see all the black arrows, yeah.
Thank you.
The virtual spin texture, you have to understand it like this. It's more a tool to understand why this effect is so large.
Okay.
Yeah.
Okay, so who has the next question? Smriti Chawla. Smriti, please ask.
Hi, I really enjoyed your talk, ma'am. My question is, like, what are the technical advantages of this topological Hall effect or anomalous Hall effect? Like, we are particularly looking for topological Hall effect. Are there any specific advantage for that?
No, wait a moment. So the advantage of the anomalous Hall effect in general, as I said, is related to a spin polarized current. And the topological Hall effect is also related to a spin polarized current, but the spin is not anymore a good quantum number since the spin is changing. While the electron is moving, the spin is changing. Spin direction is changing since you have a non-collinear system. And in this respect, if you ask for advantages with respect to data storage devices or so, there is actually not a big difference since there is more so the signal would be the same finally, but there is more the question how to store the information. And in this respect, of course, the skyrmions are very are favored. And so in this respect, also the topological Hall effect plays an important role. Does that answer your question? Maybe I didn't understand it correctly. Are you happy with my answer?
All right. It's all right, ma'am.
Okay.
So maybe a short remark on Smriti's question and your answer, Ingrid. Isn't it like the topological Hall effect is little bit, if we really want to compare the magnitude, isn't it? It's a little bit smaller in magnitude compared to the anomalous Hall effect. It is possible. Yeah, it depends
on your system.
Yeah, that's true.
And usually, since the skyrmion system has also a total moment, usually they are superimposed, and it's complicated. You measure a hysteresis loop, and then when you want to analyze it, you have to subtract the anomalous Hall effect, and then you have this bump that is related to the topological Hall effect. Yeah, also the signal is usually you are right in these standard systems. The anomalous Hall effect is larger than the topological Hall effect. But the message from my talk is that the anomalous Hall effect of these coplanar antiferromagnets is even larger than in ferromagnets. This was predicted and also found. But so from my theoretical point of view, I only wanted to say, don't worry. We call it an anomalous Hall effect since we calculate it the same way as an anomalous Hall effect, but the insight tells you there is something like this spin texture that you have, this tilted spin, this virtual spin texture is something that, like a little skyrmion, a very little skyrmion, only 3 atoms. You know?
Okay. Thank you. So are there any other questions?
Yeah, I have one question.
Please.
First of all, thanks for this nice talk. I just thought about the fact that we can make the magnetic structure coplanar by external field, where we can suppress topological phenomena. So whether such field-dependent Hall measurement could distinguish that topological one from this anomalous one in high field. obviously.
Now I have to, maybe I should say that you cannot, if I'm here in my slide, you cannot, so this angle this tilting angle, this is not a tilting angle that you can easily generate by an external magnetic field. Since these are different phases, so of a material. It's only in a theoretical description that I can use it as a continuous parameter, but in reality, this phase would be a different material from the 45-degree phase, for example.
Okay.
Yeah.
And one more thing I was thinking, that the contribution of the Hall transport due to the skyrmion formation and the scattering of the conduction electron from that skyrmion structure that gives the topological one, right?
Can you repeat it? I didn't understand it.
I mean, the Hall effect from the scattering perspective, I'm saying. So electron is moving and we have a real space skyrmion structure, and that gives additional transverse movement of the conducting electrons. That is the so it is real space. When you map it to the momentum space, you have equivalent vector potential added to your Hamiltonian. The point I'm here thinking, like when there are some experiment where the charge can make the skyrmion mobile. So in that case, how intact the skyrmion lattice you can think of? I mean, it can be destroyed by that charge current.
Yeah, it can be destroyed. It's a question of the charge density, actually. Yeah, you are right.
And then how the Hall transport must have the dependence of the current then?
Wait a moment, this I didn't understand.
I mean, if the skyrmion structure is destroyed by the applied charge current, then the topological Hall current, the Hall transport has some current dependent terms.
Yeah, then the topological Hall effect would disappear. But I mean, so there are two contributions to the topological Hall effect. This I would like to repeat. There is a topological Hall effect that you observe from a single skyrmion, which is the analog to the spin Hall effect that I have been discussing in the beginning, or the anomalous Hall effect for band electrons. And then there is the quantum topological Hall effect that I discussed extensively during my talk, which is related to the edge states in a skyrmion lattice. And this is something on top. You would usually, the quantum topological Hall effect was not yet measured.
Yeah. Okay, I mean not the quantum topological. I mean just talking about the skyrmion lattice that you form, that can be destroyed by the charge current.
Yeah, but then still, the skyrmion lattice can be destroyed. But as long as you have a single skyrmion, then of course the topological Hall effect, the topological Hall signal that you measure is related to the skyrmion density.
Okay.
And so with the current, you destroy the skyrmion lattice, but you would still have individual skyrmions, but with reduced density. So your signal would change with the current.
Okay, the density that preserved.
Yeah.
Okay. Thank you.
Okay, is there any more question?
Yes, I have one.
Yeah, Braj, please.
Very nice talk, ma'am. So my question is related to the Barry curvature. As experimentalists, can we quantify Barry curvature?
No, you cannot measure it. It's a field that we introduce to simulate in a semi-classical manner spin-orbit interaction. And so spin-orbit interaction is, of course, the interaction of the orbital motion of the electrons and with the spin, so from the orbital motion, and in particular, it's like I said, it's like a force field that can only be measured in an indirect way by this transport coefficients.
And
A direct measure is it's in German I would say a Hilfsfeld. It's something that I introduced to explain the whole thing, but it's nothing that it's not an observable.
And what defines its strength actually? It's a gauge field. So what defines its strength actually?
The strength is the strength is defined by if you remember the formula. The strength is so in the formula I discussed that in the denominator was a difference of energy eigenvalues, and then it means the Berry curvature is going to be very large if these energy eigenvalues are very similar, if they are nearby. And so this you can understand in the following way. I discussed the motion of one electron in one certain band, but there are other bands and other electrons in the other bands. And the force of these other electrons is described in the Berry curvature field. And as soon as my electron comes nearby to my band that I consider is touching nearly, or I have this avoided crossing, another band, then this force is very large. So the Berry curvature field, you can imagine like the field of a point charge. It looks like the field of a point charge if you would put your point charge in the crossing, in the Dirac point. So maybe I could go back to this slide. I don't have it in. Yeah, here. This slide, here you see. So the Berry curvature is particularly large in these. Here it was a crossing. So there is no Berry curvature calculated for lambda equals 0, but here's a crossing. And then I get this avoided crossing, which gives rise to a large Berry curvature. And also here you see so avoided crossing, large Berry curvature. The Berry curvature is the larger, the nearer the bands, or the nearer the other bands that I do not consider in my semi-classical description.
Okay, so can we say it is directly proportional to the spin-orbit coupling?
Sorry?
Can we say the strength is directly related to the spin-orbit coupling?
No, this is not, you cannot map the Berry curvature to the spin-orbit coupling. You can calculate a so-called spin-orbit coupling field, which is not equivalent to the Berry curvature field. No, you cannot say that.
Okay, I have another
question. I wanted to give you another explanation. So you can forget about the Berry curvature and do a quantum mechanical calculation, fully quantum mechanical calculation of the conductivity tensor by Kubo formula. And in the Kubo formula, you would take into account also all bands, and you would have contributions from the individual bands, and you would have contributions from interband transitions. And these interband transitions are particularly large, or give a large effect to the conductivity as soon as the bands are very nearby. So strong Berry curvature would mean in a quantum mechanical picture interband transition, which I do not consider in a semi-classical description.
Okay. Okay, I have another question. When you use skyrmion field,
Just a quick one.
Yeah.
Okay. Because I have another meeting and Zoom, we are booked only to 4:30.
Okay, okay.
Please make a quick question. That's okay. Please go ahead.
Yeah, so you used a skyrmion field. Is it you are talking about the field generated by a single skyrmion?
Sorry?
You have used a skyrmion field, say you are saying
This
skyrmion.
emergent field, you mean?
Skyrmion field. So is it the field this is generated by a single skyrmion that you
No.
are talking about?
No. As I said, so this emergent field is not the magnetic field of the spin texture. The emergent field is really the Berry curvature field in real space. It's related to the skyrmion number.
Oh, okay. Thanks.
Okay, thank you. I think we need to move on. Ingrid, could you kindly stop your screen? I like to share my screen to present a small digital plaque from our team.
Yeah.
Okay, so here we go. Just a second. Share screen. Okay, so do you see my screen now?
Yeah.
Okay, so thank you so much for your excellent talk. I think very rigorous discussions, people enjoyed. And on behalf of our team participants, we like to present you this digital plaque. I just read it for you. W2S seminar, webinar series on spintronics. Mysore, Bhubaneswar, India. Takes pleasure in presenting this plaque to Professor Ingrid Mertig from Martin Luther University in Halle, Wittenberg, Germany. In recognition and appreciation for being a very valuable speaker to give a lecture on transversal transport coefficients and topological properties. Thank you so much, Ingrid, for your generous time and talk. We really enjoyed, and we hope that maybe next year we will be able to welcome you in our campus in India or I meet there in Germany. So either way, really looking forward to that. And please stay safe. And I also request you and your group, if you have time, kindly feel free to join our seminars. And next week, we will have the seminar by Professor Bukhari-Lipnitz. Same time, Thursday. Thank you so much. Take care. Bye-bye.
Bye-bye. Thank you.